These volunteer astronomers at Chabot Space and Science Center in the Oakland Hills are on a mission. They've joined a quest to find what, for many, is the holy grail of space exploration. A planet outside our solar system, capable of sustaining life.
You don't have to be a professor or work for NASA to do this work, because we can train the amateurs to be able to do it. They'll never forget that experience. I mean, you got to say, it's pretty exciting to actually use a telescope like this. And of course, we do have sometimes where we'll look at real objects like, Saturn and Jupiter. But on the whole, we rarely look at anything else. We look just for exoplanets.
Exoplanets are planets orbiting stars other than our own sun. The closest are trillions of miles away. While astronomers at Chabot play a big role in exoplanet research, actually finding them is like searching for a needle in a million haystacks.
When you look up in the night sky, you're seeing some of the 200 billion stars just within our Milky Way galaxy alone, and there are hundreds of billions of galaxies.
In that vast expanse of space, making the initial discovery of an exoplanet orbiting a faraway star takes more than an optical telescope. Planet hunters like Professor Jeff Marcy and his team need specialized equipment found only at larger observatories, such as Keck in Hawaii or Lick Observatory atop Mount Hamilton near San Jose.
We are really fortunate that here in the Bay Area we have one of the world's greatest observatories. At Lick Observatory we have a telescope with a mirror that's 3 meters in diameter, but we're building a new telescope that has a mirror the size of the Hubble Space Telescope. And that telescope will be used every single night, night after night, hunting specifically for other Earths.
The first exoplanet was discovered in 1995 by a team from Switzerland. It was a revelation. Suddenly, the presence of other worlds went from theoretical science fiction to science fact. Today, a Bay Area team of astronomers is blazing the path.
As soon as we heard about the Swiss report, we quickly analyzed all of our data that we already had on hard disk, and we found 2 planets of our own. We quickly found the next 10 planets within 6 months. And now at this current era, we have about 250 planets known around other stars and counting.
Finding these planets is actually very difficult. The planets themselves are so dim that they're lost in the glare of the star. What we do is we rely on the laws of gravity, the laws of physics. We know that as that planet is orbiting the star, that it's tugging the star around a common center of mass between the 2 objects, between the star and the planet. But because of that, the star wobbles around with the same period that the planet takes to go around the star itself.
Detecting the wobble of a star due to a planet orbiting it, yanking on that star, is extraordinarily difficult, so it's almost undetectable. Picture an astronaut on the moon. An astronaut holding a quarter up on the moon, seeing that quarter edgewise, that's the amount of motion we would see it from here on the Earth, that a star moves due to its planets.
So how do you detect a celestial wobble that's so infinitesimally tiny?
The technique that we use to find extrasolar planets is called the Doppler technique. We're watching the frequency of the light change. You can imagine this experience if you're sitting on a boat in a lake and the waves are going by under you with a certain frequency. I always have my students do this. And now you turn on the motor of the boat and you drive into the waves, then you hit the waves more quickly. And you turn the boat around, so you're driving in the same direction that the waves are traveling, and now it goes more slowly. That shortening and lengthening that we measure, of course that wave isn't really changing length, but it appears to change length because it's moving toward us or away from us.
To measure those light waves, astronomers use a spectrograph to separate and spread the light from a star into a long rainbow-like code. A computer then isolates the subtle differences in light waves over time, and astrophysicists analyze that data to tell if a star is wobbling.
The real trick to planet hunting is to break up the white light from a star into all of its composite colors, blue, green, yellow, and red, the colors of the rainbow. And in fact, we break up the white light from a star into about 1,000 different subcolors, or wavelengths of light as we call it. We have to detect the change in those colors due to the star a-coming or a-going to about 1 part in 100 million. This is a little bit like having a piano with all of its keys, each key producing a different note, but now changing the note that each key plays by 1 part in 100 million. C wouldn't become C sharp, C would just be 100 millionth of the way towards C sharp. That's the degree of precision with which we have to measure the frequencies of light waves to detect our planets.
Only a relatively large planet will create the kind of gravitational shift in a star that can be picked up from trillions of miles away. So that leaves all the smaller Earth-sized planets unaccounted for.
We found the first few hundred planets. They were Jupiter and Saturn size. Now the questions have changed. We really would like to find other Earth-like planets. We haven't found any yet. It's not because the Earths aren't out there. It's because Earth-like planets are so little. In fact, our own planet Earth is 1/300,000th the size of our sun. So finding Earth-like planets is much more challenging than finding the bigger planets.
If you think of these exoplanet hunters as the explorers pushing boundaries and seeking new frontiers, then the astronomers at Chabot can be called the settlers. Once they know where an exoplanet is, they move in.
There are many of us, which you call the settlers, out there in the field who are now looking to see if there's a transit of a planet in front of a star. And that's very important to the Jeff Marcy group because they then take our data and they get some idea of how many planets, how big the planets are, etc. So we're part of a big team that all around the world.
Once astrophysicists determine a star's wobble, they can deduce when an exoplanet may cross in front or transit its parent star. Observers at Chabot then watch to see if there is a change in the visible light.
It's a very small effect. These stars are 60 to 200 light years away. You know, 1 light year is 6 trillion miles. These are very far away. If we could see the planet affect diminishing the light of the star, we can get an idea of the size of the planet and get an idea of its orbit. Once you have the size and you have its orbit, you can get the density. And that's very important because now once you have the distance and the density, you can get an idea whether it's a rock planet like the Earth.
The quest for extrasolar planets is really focused right now on the search for Earths. Earths that exist at a distance from the star where it's not too cold so that all the water's frozen, not too hot so that all the water's been vaporized away, but in this Goldilocks zone that's just right where liquid water could exist.
Scientists call that area the habitable zone. In April 2007, a rocky exoplanet was discovered 20 light years away. While it's larger than Earth, this planet orbits its star at a range that may harbor life. Still, Earth-sized planets have remained elusive, but that's about to change. Scientists at NASA Ames Research Center in Mountain View are developing a new satellite telescope designed specifically to look for Earth-like exoplanets. Known as Kepler, the mission is set to launch in 2008.
The idea is simple. It will take picture after picture of the constellation Cygnus and watch for stars in that constellation that dim when an Earth-like planet crosses in front of the star, blocking some of the starlight. Then the planet goes on its way and it'll block the light again and again and again. So you'll repeatedly see a star dim if an Earth crosses in front.
The Kepler satellite is going to have a big telescope that looks at 10,000 of these transits at a time, or 10,000 stars at a time. That's really something. Plus the fact the instrumental methods are getting more sensitive, so we're getting to smaller sized planets all the time, down very close to Earth size.
Finding Earth-like exoplanets doesn't mean we'll be going there anytime soon. Even with the fastest modern spacecraft, it would take thousands of years to travel to the closest extrasolar systems. But advances in technology have made this one of the most exciting times in astronomy. There's a sense that some of the greatest discoveries may be lingering just beyond the horizon.
I think it's in our genes that we look up at the night sky, look at the stars, and wonder, can we travel to the stars? Can we find other habitable worlds? Can we find our kindred spirits, other creatures out there who can tell us about their cultures, their learning, their music, their poetry? And in so exploring, perhaps we will learn a little bit more about where we came from, why we humans live our lives, and where our roots are here on the Earth.